In the late 1460s, a massive merchant vessel was navigated into a tidal-side channel off the River Usk in Wales. The crew maneuvered the ship on a high tide, intentionally grounding it over a heavy timber cradle for a critical refit. As the tide receded, the enormous weight of the hull settled onto the wooden supports. Before the structural repairs could be finalized, the timber cradle gave way, collapsing, shifting, or deforming under the load. The hull heeled hard to starboard, and the lower planking drove down into the dense alluvial mud of the riverbank, locking the ship in place before anyone could recover control. The exact mechanical sequence of the cradle collapse remains unknown. Today, this wreck is identified strictly as the Newport Medieval Ship. The stakes surrounding its modern excavation were absolute. The mud had preserved the timber in a low-oxygen, waterlogged state for centuries. But once exposed, the wood would deteriorate rapidly unless it was kept wet and moved immediately into conservation, especially because corrosion products from iron fastenings can drive damaging chemical reactions in saturated oak. When the heavy ship rolled off the cradle in the 15th century, the crew lost all physical ability to upright the hull. The River Usk features a massive tidal range. The cold, muddy water quickly surged over the fallen starboard side, flooding the lower compartments and sealing the massive ship tightly against the riverbed. Contemporary workers recognized the ship was effectively lost. They stripped what they could reach, rigging, fittings, and any accessible upper structure. And at some point, the exposed port side appears to have been cut down low, leaving the broken lower hull to sit sealed in the mud. Exactly how much was removed and whether the cutting was driven by salvage, later riverbank works, or both, cannot be proven from the surviving record. The River Usk carried heavy loads of fine silt. Day after day, the tidal flow deposited fresh sediment over the abandoned remains. The starboard side was already driven deeply into the earth by the blunt force of the collapse. Slowly, the alluvial mud swallowed the remaining lower timbers entirely. How deep the wreck ended up buried is uncertain, but it was sealed beneath heavy sediment for centuries, creating the low oxygen conditions that help preserve the wood. And while parts of the wreck show evidence of past disturbance and cutting above the mudline, the surviving lower hull remained deeply buried until June 2002. Heavy construction crews arrived on the west bank of the River Usk to begin a major urban development project. Structural engineers were tasked with excavating a deep foundation pit to accommodate the sunken orchestra level of the new Riverfront Arts Center. The site was enclosed, sheet piled, and stabilized as new piles were driven for the build. In that process, some of the modern works cut into buried medieval timbers. Before the full scale of the wreck was understood, the heavy concrete columns punched violently through the buried oak timbers. As the mechanical excavators moved in to dig out the deep mud pit, the steel buckets scraped against massive, radially cleft planks. The construction operation was immediately aborted. Marine archaeologists descended into the wet, muddy foundation trench to inspect the damage. They found the heavy oak frames and overlapping planks of a remarkably intact lower hull protruding heavily from the trench walls. Modern concrete piles had already punched localized wounds into the structure. The engineering team and the archaeologists now faced a massive logistical trap. The ship had to be removed to allow the city project to continue, but extracting the fragile, waterlogged wood from the deep foundation pit presented an extreme physical challenge. For more than 5 centuries, the mud kept the oak airless and stable, but the moment it came up into open air, the countdown would begin. The engineering reality of a medieval merchant vessel is that much of its surviving strength depends on an intact hull shell. Modern recovery crews faced an immediate geometry trap in the foundation trench. They could not safely pass heavy lifting straps beneath the submerged lower hull to attempt a clean, single-crane recovery. The vessel measured an estimated 116 feet in original length with a beam of 27 feet. Lifting a waterlogged wooden artifact of this sheer scale in one coordinated piece demands rigidity. Yet modern concrete piles had already punched through key structure, leaving the hull too compromised for any all-in-one lift plan. It would have to come out in sections. The fundamental architecture of the vessel created a severe extraction constraint. The hull relied entirely on clinker-built shell geometry. In this highly specialized construction method, shipwrights establish the hull's form through the outer skin first. They assemble sweeping, overlapping oak planks, fastening the seams tightly with wrought iron clench nails and rove plates to create a rigid, watertight shell. And only then is the internal framing brought in and fitted to reinforce what the shell has already defined. To seal the overlap joints and prevent water ingress, the original builders applied a dense conifer tar luting between the adjoining strakes. Because the heavy internal frames are only dropped into the hull later for secondary reinforcement, the structural integrity of the entire ship is completely dependent on the continuous, unbroken tension of that overlapping outer skin. The modern concrete foundation columns had violently severed this continuous skin tension, creating lethal weak points along the primary structural axis. Any uneven lift would simply peel the lapstrake seams apart before the hull ever cleared the mudline. The recovery team had to break the stalemate by abandoning any clean lift plan. The only viable path was controlled dismantling, sacrificing the hull's unity to preserve each timber as evidence. As they began assessing the interlocking planks embedded in the deep clay, they noticed something small but deliberate. Diamond-shaped marks cut into the inboard planking at the ends of old stress cracks. The most plausible reading is simple and practical, a stop mark, intended to help prevent a crack from running further along the grain. It is a rare glimpse of medieval repair thinking, preserved intact in wet mud. To safely clear the deep foundation trench, every single wrought iron clenched nail holding the overlapping shell together had to be carefully removed or mechanically bypassed. The recovery team prepared to separate the massive outer shell into individual, free-floating oak planks and heavy transverse framing elements. Disassembling the vessel eliminated the risk of a single lift collapse, but it opened a ruthless documentation problem for the marine archaeology team. A medieval merchant ship possesses absolutely no straight lines in its architectural design. Every primary oak timber is heavily curved, shaped by axes and radially cleft to match a highly specific three-dimensional position along the exterior hull. Breaking the clinker tension would instantly release centuries of locked mechanical stress, allowing the saturated, waterlogged planks to immediately flex and permanently lose their original manufactured shape. The archaeologists recognized they had to destroy the physical structure of the ship to save it, but dismantling it meant losing the exact spatial relationship of 1,000 curved components. Traditional archaeological photography and manual tape measurements fail entirely when documenting a complex three-dimensional lapstrake hull. The recovery team faced severe sensor limits in the muddy, active construction trench. They were preparing to dismantle the heavily distorted structure into as many as 1,700 primary timbers, along with many additional smaller fragments. The moment the wrought iron clench nails were severed and the physical tension was broken, as every single oak plank would instantly lose its structural context and flex out of its original orientation. To prevent the permanent loss of the ship's complex architecture, the archaeologists needed to map every inch of the waterlogged wood precisely as it rested in the mud before a single piece was moved. The traditional methods of sketching and string lines were simply not capable of capturing the sweeping, overlapping curves of the 15th century merchant vessel. To achieve a flawless digital dimensional lock, the marine archaeology team deployed advanced industrial measuring equipment directly into the wet foundation pit. They utilized a Faro digitizing arm, a highly articulated multi-axis mechanical sensor that records exact physical coordinates in three-dimensional space. By physically tracing the contact probe of the Faro arm over the surface of the submerged timbers, the team streamed continuous, sub-millimeter geometric data directly into specialized Rhino three-dimensional modeling software. The engineers maneuvered the robotic arm around the heavy structural damage caused by the modern concrete piles, mapping the intact sections with extreme precision. This process generated an exact digital twin of the entire lower hull. The mathematical model locked in the precise curvature of the wood, the depth of individual medieval tool marks, and the exact spatial location of every iron fastener impression across the entire exposed structure. That sub-millimeter model locked the hull's geometry before a single timber moved, and it would later let conservators calculate shrinkage and warping during reassembly. With the footprint secured in coordinates, physical disassembly finally began. The archaeologists systematically extracted the surviving outer hull, carefully separating the heavy, saturated oak components from the deep alluvial clay layer by layer. The manual labor was grueling as the deeply buried lower timbers had absorbed massive amounts of water, drastically increasing their physical weight. As the deconstruction phase accelerated, the massive operation immediately encountered a severe logistical threat. Stripping the ship generated a massive volume of dark, waterlogged, visually identical oak fragments. Maintaining a strict forensic chain of custody for every single extracted piece was an absolute operational necessity. Standard archaeological paper labels and modern waterproof markers dissolve or detach completely when submerged in long-term wet storage. To solve this critical tracking failure, the salvage team utilized bright plastic agricultural cow ear tags. They nailed these heavily industrialized, indestructible plastic identification markers directly into the ancient wood. This aggressive but highly effective tagging system locked a permanent tracking number to each of the 1,700 isolated components, guaranteeing zero loss of identity as the heavy timbers were hoisted out of the trench and transported away from the Riverfront Art Center foundation pit. The heavy excavation machinery finally cleared the empty mud trench, allowing the delayed urban construction to resume above the riverbed. The entire physical mass of the medieval vessel was now fully cataloged, isolated, and submerged in temporary wet storage tanks to prevent immediate atmospheric drying. The complex, interlocking geometry of the great ship was mathematically secured on hard drives, but the physical timbers were now completely exposed and saturated with an invisible, highly acidic threat. Once the timber mass was out, hundreds of pieces, plus countless fragments, the wood carried a hidden chemical burden. For more than 5 centuries, wrought iron clenched nails and rove plates had been corroding in oxygen-poor clay, driving soluble iron salts deep into the oak's cellular structure. Exposed to air, that iron could react and accelerate long-term internal decay. To blunt the risk, the conservation team moved immediately into extended ammonium citrate chelation baths, with repeated rinsing cycles to drive down soluble iron before the next stabilization steps. This intensive desalination phase successfully neutralized the immediate chemical corrosion threat. However, the conservation team still had to overcome an extreme physical vulnerability. Centuries of deep burial and saturation had dissolved the original cellulose walls deep inside the oak structure. The structural voids were entirely filled with cold river water. If this internal moisture was allowed to evaporate naturally, the intense surface tension of the receding water droplets would pull the degraded cellular walls inward. The microscopic cells would completely collapse, shrinking and violently warping the massive timbers until they cracked apart. To prevent this mechanical failure, the marine archaeology team executed a highly complex sequence of cellular bulking. The heavy timbers were removed from the ammonium citrate baths and lowered into a new series of heavy containment tanks. The conservation engineers flooded these vats with highly concentrated solutions of polyethylene glycol. This heavy synthetic polymer acts as an industrial stabilizing agent. Over an extended soaking period, the polyethylene glycol molecules slowly penetrated deep into the heavily degraded oak structure. The dense polymer physically displaced the ancient river water, filling the microscopic cellular cavities and providing rigid internal support to the fragile wood. While the polyethylene glycol successfully bulked the cellular walls, a significant volume of water remained trapped deep inside the massive timbers. Standard heat drying would still trigger a catastrophic surface tension collapse. To safely extract the final moisture without destroying the wood, the salvage team required advanced industrial hardware. They transported the chemically saturated timbers to massive vacuum-freeze drying chambers. Inside these sealed steel cylinders, the conservation engineers dropped the internal temperature far below freezing, turning the residual water to solid ice. The technicians then engaged heavy industrial pumps to drastically lower the atmospheric pressure inside the sealed chamber, creating a deep vacuum environment. This extreme pressure drop triggered a physical state change called sublimation. By precisely manipulating the internal vacuum and applying a controlled, or low-level heat source, the engineers forced the solid ice crystals locked inside the wood to vaporize directly into a gas. The water completely bypassed the liquid phase. Without the presence of liquid water, there was absolutely no surface tension to pull against the fragile internal structure. The vapor was safely extracted from the chamber, leaving the polyethylene glycol to permanently support the heavy oak structure. The last moisture left the wood without ever becoming liquid, so the weakened cells never faced surface tension collapse. With the polymer support locked in place, the timbers were stabilized against atmospheric decay, clearing the way for forensic science to extract the vessel's encrypted origin data. The physical evidence extracted from the mud exposed a stark mismatch. As the conservation team processed the stabilized wooden components, forensic archaeologists began analyzing the surviving timber to determine the exact origin of the vessel. Early assessments immediately revealed a severe discrepancy. The shattered wooden beams of the collapsed support cradle and the massive structural oak of the ship itself returned completely different physical signatures. The investigators recognized they were looking at two separate construction events, separated by thousands of miles and a significant gap in time. To mathematically separate the original 15th century merchant ship from the fatal Welsh repair effort, the scientists required an absolute biological timeline. Traditional tree ring analysis often fails when a marine artifact is built from foreign wood. The standard dendrochronology relies on matching annual growth patterns to reference chronologies. And if the timber comes from far outside the local dataset, the match can stall. To push past that limitation, the forensic team turned to oxygen isotope dendrochronology. This method can secure absolute dating by reading the year-by-year isotope pattern preserved in the wood's growth rings, and it can sometimes support broad provenance when compared against regional isotope baselines, but it does not guarantee a pinpoint map location in every case. Where the outermost rings survive, it can also hint at felling season. Where they do not, it can still lock down the felling year window with high confidence. The research team extracted samples from the massive beach keel and the primary oak strakes of the lower hull. The isotope chronology indicated the main construction timber was felled in the winter of 1457 to 1458, and the broader isotope signal points toward northern Spain around the Bay of Biscay, likely the Basque Country rather than the United Kingdom. They then turned to the shattered remnants of the support cradle found crushed beneath the starboard hull. That timber showed a different signature consistent with local British material, and the outer rings place its felling no earlier than the spring of 1468. Taken together, the evidence resolves the contradiction without pretending to recover a lost name. The ship was built shortly after the winter of 1457 to 1458, then worked the Atlantic routes for less than a decade, before entering the Welsh tidal channel after the spring of 1468 for repairs that ended in disaster. Finally, in the spring of 1468, the aging Spanish vessel navigated into the Welsh tidal channel for a heavy structural refit, where the locally built British cradle violently collapsed beneath it. The true geographic origin of the massive merchant vessel was definitively proven, yet the exact identity of the humans who commanded it remained permanently out of reach. The exact identity of the massive 15th century merchant vessel remains permanently locked behind an absolute evidentiary wall. Despite deploying advanced chemical timber dating to prove its original construction in the Basque region of northern Spain, forensic archaeologists cannot answer the most fundamental human questions surrounding the long operational life of the ship. The original name painted on the towering hull is entirely unknown. The identity of the wealthy merchant or nobleman who owned the highly valuable financial asset is completely unknown. The surviving historical record contains absolutely no mention of the catastrophic cradle collapse in the tidal River Usk during the spring of 1468. Even the precise depth of the thick alluvial mud matrix that swallowed the shattered starboard hull after the contemporary salvage crews abandoned it remains highly debated and ultimately unknown. What the modern salvage operation definitively achieved, however, was a complete physical and digital resurrection of an unprecedented maritime artifact. By successfully extracting the shattered, waterlogged remains from the deep foundation pit in Newport, Wales, the recovery team secured one of the most substantial and best-preserved 15th century merchant ship hulls discovered in Britain in modern times. The sheer physical scale of the ship completely alters the modern understanding of medieval logistics. Originally measuring an estimated 116 feet in length and capable of hauling 161 tons burden, the massive hull fills a critical blind spot in the archaeological record of naval architecture. It provides a flawless physical blueprint of heavy medieval oceanic transport just before the dawn of the global exploration age. The surviving timbers represent the absolute apex of medieval shipbuilding. The vessel was constructed at the extreme upper physical limit of clinker-built shell geometry. In the decades that followed the winter of 1457 and at different speeds across different coasts, European shipwrights increasingly favored skeleton first carvel construction for the largest ocean-going ships. A shift driven by changing demands in trade, warfare, and long-range voyaging. Lapstrake did not vanish overnight, but this vessel stands near the upper edge of what a clinker hull could do at full scale. This specific vessel survives as the ultimate, highly evolved final iteration of a dying engineering lineage. Its survival today is a direct consequence of cold, heavily calculated, and entirely unsentimental engineering decisions made during the modern excavation. The massive ship was effectively destroyed twice. It was shattered first by the fatal cradle collapse in the 15th century, and it was violently struck again by heavy modern concrete foundation piles in the year 2002. To save the vessel from total atmospheric and mechanical annihilation, the archaeologists deliberately destroyed the surviving physical tension of the wreck. A single theatrical crane lift would have snapped the damaged, waterlogged hull in half. Instead, the team relied entirely on sub-millimeter digital twin mapping to mathematically archive the exact, highly complex curvature of the original hull in three-dimensional space. They systematically dismantled the interlocking ship piece by piece, tagging the massive inventory of wood to maintain a flawless forensic chain of custody. By isolating the individual planks, and the conservation engineers successfully bypassed the fatal chemical corrosion threat and permanently secured the fragile cellular wood through a highly industrialized cellular sublimation lock. Today, the physical timber is stabilized for long-term preservation, but only under carefully controlled conditions that keep the conserved wood safe from renewed deterioration. The digital blueprints provide a mathematically perfect map for the ultimate physical reassembly of the hull. A machine of the medieval Atlantic trade network, built in Spain, sailed for a decade, and crushed in Wales, has been pulled back from the brink of modern destruction. The operation stripped away the mud, neutralized the internal metallic threat, and forced the ancient oak to yield its exact physical data.